I haven't really looked at any application of object sequence verify, so I was wondering if you could show us some applications with those. And as a company, we're looking at implementing opt in replace by fee. We were struggling a bit with the privacy aspect, adding new inputs.
Yeah.
So I was wondering if you could say something about that.
Okay. Yeah, well, I mean, maybe I'll just touch briefly on my own Python Bitcoin lib. So I'm actually a maintainer and did most of the design in the current version of the Python. I mean, literally it's called Python Bitcoin lib. It's the Python library I have for Bitcoin. I guess you call it interacting with Bitcoin. The way the library works is really, really low level. If you ever read the Bitcoin core source code, I mean, I basically take the data structures in there and I create Python versions of that, and you can just directly manipulate those data structures and so on. And I think to answer kind of your questions about how do you interact with the chain, well, with Python Bitcoin lib, I mean, it's mainly a library dedicated to working with Bitcoin core instance, right? And that you have your Bitcoin core instance. It has RPC interface, which is a standard JSON over HTTP thing. I don't really know much about web standards, but I assume that's a relatively standard type of way to do stuff. And you can go and query your Bitcoin core instance for things like, what's the current best block? Do you have any, give me a transaction in your mempool, and all the kind of basic stuff, as well as things like where are the contents of wallets and so on. And then you can, take that input data, construct data structures in Python Bitcoin lib like a transaction, potentially a block. I mean, really whatever you want to do. Scripts you can do. You do that data structure creation and computation, and you can then feed it back transactions, as well as potentially blocks. And your Bitcoin core instance go handle broadcasting the transactions, verifying that they're valid, is the UTXO set valid, and so on. And that tends to be how I do most of my work. So you have a local full node, and build add-ons to it in Python, and you use it for verification. And if you just draw this, so if you think in terms of the blockchain there, well, that means you have your block headers. Right, and each block has a tree of transactions. At the very bottom, the tree of TX. Now you have transactions. And when we talk about a full node, all we mean is that all this data is getting verified. Yes, every transaction is getting verified, every block header is getting verified, and so on. And with Python Bitcoin lib, well, since you have a full node local, that's what you're relying on to do all the verification. Whereas what Python Bitcoin lib would mainly do is construct transactions for you. As an example, if you've ever seen my replace by fee tools, it's a set of libraries to work with replace by fee. So if you have a local Bitcoin node that supports the replace by fee patch, well, you can construct transactions with the full replace by fee tools that create those data structures and do whatever you need to do, and then send it off to your local Bitcoin node.
What is the replace by fee tool?
It's the one where in your mempool, depending on which version of replace by fee you have, essentially if transaction exists in the mempool, it's not on the blockchain, and another transaction comes along that pays a higher fee, but would conflict with that first transaction because it spends the same inputs. With replace by fee, that transaction can get replaced in the mempool. And then if miners are in it, then transactions that are broadcast later can potentially get mined, even though they conflict with transactions that were broadcast earlier.
But you are saying, you are talking about inputs. Is that a different thing than, because I, as a user, think in terminology of I have my Bitcoin address and I'm paying to another address? Is there a different?
Yeah, so that'd be an output. And the replace with fee patch analyzes inputs. So it says if a new without replace with fee, if a transaction is received by your Bitcoin node, and in the mempool there exists a transaction spending the same input, as in spending a previous confirmed coin, it'll evaluate whether or not to replace transaction 1 with transaction 2 based on what pays the most fees.
So my coins are a collection of inputs?
Yes, yeah.
And the mempool, as far as I understood it, that is actually kind of like the random access memory of the Bitcoin miner running.
Yeah, I mean, yeah, the mempool is just like the set of unconfirmed transactions you know about. Transactions that aren't in the blockchain yet, could be, and you know that they exist because someone sent them.
But I mean, the mempool is not something of the blockchain. It's something living and
separate.
Updated.
And every node will have a different mempool.
Yeah.
Because what's in the mempool just happens to be what transactions you know about.
And I read that you are trying to do some research on mempools because you think that's the next big hurdle for not decentralization.
Yeah, I think you misunderstood that.
Oh, okay.
Yeah, I haven't paid much attention to mempools.
Okay, but
you might be thinking of the UTXO set.
Oh, yeah.
Yeah. The UTXO set is just the set of unspent transaction outputs. Right? So every time a transaction is put in the blockchain but isn't spent yet, that is added to the UTXO set. And I was doing research on how to archive entries in the UTXO set so it doesn't just grow and bound it. This was interesting.
Could you repeat it again?
Well, so the thing is like
UTXO?
UTXO. Yeah, unspent transaction.
Okay.
Yeah. And the thing is, like with the UTXO set, the reason why that research is important is when you receive a new block, every transaction in it will be spending unspent outputs. Well, if you can't process those spends quickly, which involves querying your local database, your local UTXO database, see if is this output actually unspent. The slower that process is, the slower it takes you to verify a block. And the slower it takes you to verify a block, the less money you're earning as a miner. Well, how do you make that process faster? Well, you put the UTXO set in the fastest storage you can get available. At least an SSD, preferably in main RAM. Well, if you have to do that to earn a living as a miner, and that then becomes your overhead. In the UTXO set, it can grow there's no limit to how big it can grow. Potentially gigabytes, potentially tens of gigabytes, terabytes even in theory. Well, if that grows big enough that you can't afford to keep that in RAM, you're no longer a competitive miner. So that's your big problem. And that's why I was looking at ways of, you call it kind of archiving. So you take things that would be in the UTXO set, you archive them, and then if someone wants to go spend that old output, then they provide proof that it's still unspent.
But the UTXO is a subset of your total blockchain.
Yes, exactly.
So if that would be terabytes, then the entire blockchain would be
potentially
enormous.
Yeah. But the biggest the UTXO set can grow is the rate of the blockchain itself.
Yeah.
Which currently is like 50 gigabytes per year.
Well, it's always smaller than.
Potentially not that much smaller.
So what percentage is unspent at the moment?
Currently, it'd be about, in terms of space, it's about, I think, would be 5 to 10%.
Oh, really?
Yeah.
But just for me as a non-expert on this field, so the more Bitcoin hodlers there are, the more unspent transaction outputs there are?
Yes. And the thing is, most of the space in the UTXO set is not high value transactions. It's like really, really small amounts. You know, most of it's actually like 1 Satoshi amounts, because people have just created enormous numbers of 1 Satoshi outputs. But you still got to keep that stuff, because someone might go spend it.
So every time you split the coin in
Yeah.
smaller pieces, you get more unspent outputs.
Exactly. Yeah. Yeah. And it's a big problem, because if you want to process new blocks, you know, you got to have that data. So otherwise, people can create money out of it.
Yeah, and that's also one question of me. I understood that every Bitcoin transaction, or most of them, are like, you could compare it like cash in the sense that I got a $5 billion and a 10 billion, and I want to pay someone 12,
Yeah.
pardon, 12.50. Then I give him 15, and he gives me $2.50 back. But I guess there are splittings of coins, but I'm always wondering, do coins only get split, or are there also mergings?
Well, I mean, transactions can spend more than 1 coin at once. You know, such your mechanism to merge.
Okay, so when you do a transaction where multiple inputs become one output, then
Yeah.
it's again.
Yeah.
Okay, so then the next transaction doesn't have to cope with the, let's say, 4 different inputs. That's
Yeah.
part of it.
If you have 2 Bitcoins and you pay 2, there will be 1 unspent output
Yeah.
of 2. So you reduce the unspent outputs.
Which is also the
Yeah,
reason
okay.
behind the discount in SegWit, right?
Yeah, well, so the discount of SegWit, the idea is create incentive to do that.
Yeah.
Because if there's no incentive, you know, as people spend their Bitcoins, it tends to be that outputs get split in smaller and smaller amounts, till at some point they become infeasible to spend. You know, it's very frequent that wallets don't do a good job of this. Because when you create an output, from the user's perspective, they don't realize that it's gonna cost them money later. And for the wallet's UI, I mean, how do you present that to the user? Like, well, if we spend more money now, we'll spend less in the future. I mean, people just don't do that kind of thinking very clearly. So SegWit is hoping to make that have a stronger incentive, but hard to say how effective that'll actually be.
Yeah, I have a multi-bit wallet where I have exactly the amount of the transaction fee left in that
Yeah.
wallet.
Yeah,
So then
Yeah.
you think, you know, why go spend it?
yeah. No, that's a perfect example.
Yeah.
Well, so the UTXO outset gets.
Yeah, okay, yeah. For the greater good. But does the UTXO set has a tendency to keep growing? It doesn't.
Yeah. Well, another thing too is, I mean, people lose their outputs. I mean, every time you delete a wallet by accident, those outputs will never get spent. You also see people using the UTXO set for things other than Bitcoin. You know, as an example, like I'm going to timestamp a document. Why wouldn't I put that timestamp in the UTXO set? Like that's a guarantee that I'll be able to prove the document existed before that certain time in the future. Because we're forcing every Bitcoin node to keep the data I need to prove that. From my point of view, the timestamp, that's great. And if it only costs me 10 cents and I'm timestamping something that might be, you know, $1 million legal case, you know, I'm not going to care about 10 cents. I'm not going to do something more efficient. I'm going to do the safest possible thing. And I could gladly spend the 10 cents to do it, even if it screws over everyone else.
Could you help me understand why you need all these unspent transaction sets or unspent transaction addresses to be able to validate the next block?
Well, so suppose you're running a node and you keep half of them. Now I'm going to come to you with a transaction, paying me money, and half the inputs to that transaction are going to be stuff you don't know whether or not it was unspent. And I claim that I have 1 million Bitcoins, and I'm willing to give you a really good deal on them.
Of course,
So, are you gonna accept that transaction?
Yeah, of course.
I mean, I'd really like you to accept that transaction. 'Cause I'd really like some euros right now. Maybe $1 million worth. But yeah, it's a big problem. And so far, the best we can come up with is something I came up with called TXO commitments, which says rather than having a set of unspent transactions, we keep track of the state of all transactions. And as things are spent, we mark them as spent. And what's clever about that data structure is, well, that creates this big tree. And as parts of the tree get spent, you can throw away the data.
Yep.
Essentially, let's draw this. Let's get back to our commitment stuff. So if we imagine a tree. Right, and we'll say suppose our tree has all the Bitcoins in the world committed to and a state of them. Well, if I go spend a Bitcoin, what changes in this tree is, so I'll spend that. That's color. There. So spend that Bitcoin. Well, the things that change in the tree is this data. Right? I mean, literally, like your memory representation of the tree, that changed. Well, because it's hashed, therefore that must have changed, and that must have changed, and that must have changed. And now, where previously, the digest of everything in the tree might have been that. Now it will be, say, OX8. Well, imagine we keep doing this, right? We keep marking off data. Well, one interesting thing we can do is if all we care about is the things that are unspent, then I can actually go discard a lot of this data, right? Because I can go keep track of, well, how many things are unspent under different parts of the tree. And here, well, there's 2 things unspent. And when it was created, there were 200 here, and then 400 there, and then 800 there. And as I spend things, that number changes. Now this number goes to, well, there's nothing unspent. There's 2 things unspent. There's 6 things unspent. Now, if your node is keeping track of that data, well, if I try to go spend a coin here, I'll come to you and say, all right, that coin, it's unspent. No, really. And your node's going to go down and, hang on a second, everything under here is spent. All right, discard that transaction, you're lying to me. Mm-hmm. Well, now that means there's less data I have to keep track of. And even though the data structure committed to this very, very big pile of data, for the purpose of determining if something was spent or not, we can discard most of it, all right, as things get spent.
Where do you keep track of the state tree?
Yes, yeah, it's a state tree.
Yeah, where do you keep track?
Well, this is a really clever thing. Let's suppose we decide to go discard old parts of the tree. When I come to you trying to spend, say, that input, we'll use one more state, we'll use blue, purple. I can go give you that data, because it's hashed, there's commitment. I mean, you know what digest is supposed to be, so if I just give you that data, I can refill, your knowledge about what's behind that. And then you can say, all right, yep, that was unspent. I'm going to now mark it as spent. I'm going to update all the data, and I'll keep my new thing. And that's the new state. But the onus was on me to keep the data, not you. So your node now operates with less stuff in memory. This might be very important if this is like 20 years worth of unspent transactions, and Satoshi comes along wanting to go spend his old coins. And that's kind of can be your mechanism to provide that.
But how do you know it's the last one? If I send you part of the tree, claiming that it's unspent,
Yeah, well,
and
essentially,
you're updating it later,
Yeah.
you're making it, your count will be 0.
well, think of it this way. Your node has this number, right? It knows that the state of transactions corresponds to this. And that's the commitment. So you have commitments to the state of all data. You don't actually have the data. And when I come to you to change the data, thereby spending my coins, I give you the data that you're missing. You know it's the right data because it's all hashed. And then you can change it, figure out what the new state would be, and then only record that state. And it's my responsibility to figure out, how do I get this data?
But the state needs also to be propagated into the other nodes.
Yeah, so you would, now when your node receives that, I mean, suppose you're mine, right, and you create a block.
Yeah.
Now it's your responsibility to convince other people that that state transition was correct. So you would take my copy of that data, put it in your block, send it to him, he would send it to her, and so on. But because, even if everyone's discarded the data, you can convince everyone that the way it was changed was correct. Because you give them it back, they can see, oh yeah, it's correct data, here's how I should have modified it. Now I know what the modification is, now I can go discard it all again. So it's a very, very powerful tool, and this is kind of how, this is sort of the type of basis that I think a lot of smart contract stuff will have, using tools like this. But, to answer your question about development, it's like none of the software exists. Nobody, I'm probably the only person who's written an implementation of this code. And as far as I know, no one's actually used any of this in production. Like, this is just how new the field is. So it's actually quite hard for me to go say, well, what should you go use to experiment with this? I don't know, you can download a screwed up Python library I have that's kind of documented and probably is wrong, but this really is like at the ground level in terms of actually doing things.
Because you can write a code, you can proclaim it, that it's doing the right job, but then all the nodes have to go and test with it. What would be the next step to get a protocol
to
like
do
this
this?
accepted?
Yeah, you got to go write a pile of code, basically. Concretely, like if I want to make this, suppose I'm the developer, I want to change this in Bitcoin. In the case of Bitcoin, I got to write a patch to Bitcoin Core that implements all this stuff. Got to convince other developers that it's a good idea. They'll merge into Bitcoin Core. At some point, we release software, try to convince everyone else in the world to run it. And maybe at the end of that stage, now everyone has to run this code as part of the protocol. We could add this, for instance, in a soft fork, where new rules are added. So previously nodes didn't have to keep this big tree. In the future, maybe the rule is that they do. And this entire bit of code, every single thing it does can only make a previously valid block invalid. Right? Because if a block is valid before, every additional thing this idea does could only make it invalid. Right? Because maybe it doesn't have the right commitment in the header. Maybe it's manipulated the tree in the wrong way. All that stuff is things that can go from valid to invalid. Nowhere in this proposal am I saying that something that was previously invalid is now valid. So that's your route to upgrading everyone to use this. But this could be like a 2-year project. Like even just writing my initial implementations in Python probably took probably a solid 2 weeks worth of work, and it's nowhere near good enough to use in production. If you wanted to play with it, this is under github.com/proofchains, and then this would be in Python-proofmarshall, if I remember correctly. If you Google proofchains, you'll find the code for this, but it's so early, I can't. Proofchains.
Proofchains.
Here. So that should be on GitHub. in this particular thing, what's called, well, there's something a little more complex than this called MMR, or Merkle Mountain Range. But it's all very new. And the other one is, where is it? So that's my library for just more generic Bitcoin development. Python Bitcoin lib.
There's other people maintaining different libraries.
Yeah, like for Java programmers, the big one is Bitcoin J. And that's the one that does SPV. So, key thing is with my library, you could write an SPV node in it, but nobody has. And so it relies on talking directly to a Bitcoin Core node. And it would work with Bitcoin Classics too, but I don't know if anyone's ever tested it.
So
With Bitcoin
what's
J.
an SPV node?
Right, so with Bitcoin J, what SPV is doing is it's saying, I will assume that the longest chain of block headers that I see, with the most work done, is valid. And I will just trust miners blindly. And whatever I see, I will assume is correct. And then if I want to say, determine the state of transactions in my wallet, I'll just ask nodes, hey, could you run a filter called Bloom filter against the blockchain and return me things relevant to my wallet. And that model is fairly efficient for you. All right, because keep keys, you can tell your peers, hey, give me transactions related to these addresses. You see the transactions, if everything goes well, you add them to your wallet and spend outputs and create transactions, spending them and so on. Problem is you don't know if the blockchain is actually valid. And as an example, I can go create, and I've actually done this before, I can go create a transaction that spends coins that just don't exist. And an SPV node, because it doesn't verify the blockchain, can't detect that. And in fact, I wonder if I still have it. I have it on my phone here. I've got where is it? Yeah, I've got an SPV wallet. Yeah. There we go. Yeah, this is good fun. Needless to say, I didn't actually send 21 million Bitcoins.
Are you supposed
But like this wallet, because all it has is block headers, it just doesn't know if that's a valid transaction or not. It just assumes it's valid, so it receives it. Oh, great, 21 million, done.
Okay, so but normal SPV wallets connect to multiple nodes. I suppose you didn't let it connect to random nodes.
Well, the thing is, even if it connects to multiple nodes, how does it know that it wasn't just that, say, 3 people lied to it? And that's exactly what I did in this case. I ensured that on my network it would end up connecting to, at least like 2 or I think I did like 2 or 3 different nodes that would give it the same lie. And then the other nodes, they can't tell it that this transaction is invalid, right? Because the protocol doesn't currently support that. They can only tell it, I think this transaction is valid. And once it's in a block, if miners decide to change the rules, all bets are off. Your SPV node is going to see, oh yeah, that's a block, valid proof of work. It's in the chain that I think is longest, I'm going to assume it's real. Concretely what that means is, well, if miners want to change the inflation rate, for example, make more Bitcoins per block, from the point of view of an SPV node, they can. Because SPV nodes don't check any rules. And it's not really clear to us, how secure do we need this system to be? I mean, if we assume that miners are honest and do what we want them to, then we don't need to check, because they're honest. They're not going to lie. If we assume that miners might conspire to change the rules, then we need to check this stuff, because, I mean, how else are we going to tell miners not to create money out of thin air? Chances are the truth is somewhere in between, but we don't really have a strong understanding of where it is in between.
So what is the actual use of the SPV node or the Merkle tree that is sent to the SPV node?
It's just to go verify, is this transaction something that miners have confirmed?
All right.
Concretely.
Yeah, could you show it?
Yeah. Let's go back to the blockchain again. So, the SPV node will always see this, which is, block headers. Just a second. Alright, and this part's a Merkle tree. Finally, a transaction. So it's got inputs, it's got outputs, and we have parts of the Merkle tree. This isn't really the tree, it's rather half. And the idea is that we take the tree, we throw away most of it, and then we have a path going from our transaction up to the block header. And that's really, all that SPV node sees. Because it had more of this data, well, it would just be too much data, you might as well verify. But because we're only looking at a very small part, it's running a lot more efficiently. That might be, say, a kilobyte worth of data, that might be a few more kilobytes. This is like 30 megabytes of all block headers up to history. Really not a big deal. And this Merkle path is just telling you, hashing power, thought this transaction was valid. If you trust them, we're good to go. And if you want to make a transaction, say spending that output, well, you got that data, you make your new transaction, you link that output, you go put in your new addresses and so on, and you take this, sign all these inputs, and then just broadcast it to the peer-to-peer network, which I'll go draw a nice cloud. Yeah, and eventually you might go see this in another block. And what you would have done is told one of your peers, again in this nice cloud, I am looking for transactions with this transaction ID or that spend or create, say, these outputs. And that corresponds to your wallet. This is probabilistic data structure known as a Bloom filter, which, if you're familiar with hash tables, it's kind of similar, where you kind of get this big set of bits. Everything you want to put in the filter, you hash. You assign that deterministically to one of the bits. You set it to a 1. And then when your peer checks, repeats that process again every time the data matched to the 1 bit, the bit that was set, it assumes, all right, that may have matched, and it sends you back that data. So what you might get from your peer might be, transaction you wanted, and maybe, 1 or 2 other transactions elsewhere in the tree that aren't relevant to you. And you just discard this stuff and keep the stuff that's relevant. Adds a very, very small amount of privacy.
So, can you take this, put it more? sorry for the interruption. But, yeah, not too much, but a little bit, yeah. By the way, you are on YouTube now, so you are a famous YouTuber. So, yeah.
So maybe here's an example. We could go through what's something you think you might want to do with an SPV wallet. Anyone have any projects? Maybe we could walk through like how that might actually concretely look.
Just not there, just trying to understand how you could compromise. So I haven't got that yet. Couldn't wrap my mind around.
Well, so if you want to talk about like how that compromise works, you know, with security software, what's different about it compared to normal software is, you know, when I'm writing like a text editor, all my thought process is what can I allow the user to do, right? You know, think about features. Maybe a nice feature would be like search. Maybe a nice feature would be a replace function, you know, replace one word with another. Maybe I want to have something that'll like format it and make headers or whatever. You know, these are all like features, things that want the user to be able to do. But I'm not thinking about what I want to make impossible, right? Because normal software is all about possibilities. Security software is all about preventing things from happening. You know, if you're an architect and you design a window, well, all right, what do I want to do? I want to be able to go see outside. Or the security guy is thinking, well, how do I stop people from getting inside? You know, how do I frustrate the user I don't want, which is the guy who's trying to break into my apartment? Or in the case of like SPV, you might be thinking, well, what do you want to prevent people from doing? You don't want people to be able to give you fake transactions easily. Because if I can just send you a bit of data that claims it has 21 million Bitcoins out of thin air, I mean, that doesn't sound very good.
Where is that in the picture, the 21 million?
Well, let's suppose, let's suppose this transaction, all right, inputs, addresses, and value. Well, if this is like your address, all right, I can go put in this field anything I want, like, yeah. All right, 21 million Bitcoins is a valid number of Bitcoins, and if it isn't, I'll just do 21 million minus 1. In the inputs, well, all an input is there's two fields, all right? Right, the hash of the transaction spending and sig. The problem is that hash does tell you nothing about the transaction. You know, you have no evidence that this transaction is real, let alone that it was only spent once. And the signature, well, I mean, if you don't know what the output is, how do you know that the signature is valid? Again, you can't verify any of this. You can verify this. You know, if this transaction were real, it would go pay you, and it would give you 21 million Bitcoins. But that's all you know. I mean, this is just data. I can go make 10 million of these data packets a second, even in Python, with Python Bitcoin code. You know, it's meaningless. If you see it in a block, at least you know that a bunch of hashing power went to a lot of effort to put that data in the block. But you still don't know anything about, is that data valid? So, you know, the question is, so if you don't see it in a block, I mean, who can create that? Like, what type of attacker could create a fake transaction if it's not in the block? Yeah, anyone. Anyone can create that bit of data. Now, if it is in a block, what type of attacker can create that fake data?
Miner.
Right. So you need to have some hashing power. Well, if I successfully convince you to give me 21 million Bitcoins worth of stuff, I mean, how much does it cost me to go create a fake block? It should be the equivalent of like 25 Bitcoins. Obviously, I am earning a heck of a lot of money defrauding you. So even though I have to create a fake block, it's still my incentive to do so. The other problem is, all right, let's suppose rather than 21 million, let's suppose that's 1 Bitcoin, right? So I created 1 Bitcoin out of thin air. Now, it cost me 25 Bitcoins worth of work to create that fake transaction. So obviously it's not worth it for me to do so, right? Can you think of a way that it would be?
Like 25.0001 Bitcoin.
Well, let's suppose you see a transaction in a block, and it creates, and it supposedly pays you 1 Bitcoin, right? Now, if I'm the attacker, do you think I have an incentive to create a fake block just to defraud you for 1 Bitcoin? All right, so I'll agree. Now, can you think of a way for me, the attacker, to make it financially viable to do something like that for people?
You can put 26 of these messages in your block.
Yeah. And the problem is, as an SPV node, well, you don't know how many of these messages actually are in the block. You only have 1. There could be 100 other fake transactions. Yeah, that's ultimately, I mean, you're trusting people to be honest. And it's just not clear, like, at what point does this become a bad assumption? On the other hand, if it's a full node, I mean, I could still go and do a double spend. I mean, I could start with, say, 100 Bitcoins, create an invalid block, create a valid block that gives you all, gives 26 people 1 Bitcoin. And then I could hopefully try to get another block that double spends it. So, I don't know, it's not really clear what the security model is there either. But presumably, I mean, this frankly is like a big avenue of debate in the Bitcoin world. If you make your assumption that your attacker doesn't have access to too much hashing power, and you try to force people to verify the rules, hopefully no attacker can construct a scenario where they earn money doing this. But I mean, you guys look a bit confused here as to why that's true, and well, don't worry, we are too. It's not actually clear that a lot of this stuff's actually secure, depending on how your assumptions work.
But how is the full node actually checking the inputs? Because you have a hash and a signature, and how do they look it up?
So this goes back to your UTXO set. Right?
Yeah, so you look the hash up in your...
Yeah, so your UTXO set's this big table.
Yeah.
Alright. Hash.
You should take the bottom of
The
the
number.
It's
Say script.
your bottle is in the.
Yeah. So this number corresponds to the hash. I forgot to mention it's also the index number, like this is 0, this is 1, and so on. And you've got that thing. You got the script, pub key. You check it against the signature, and then you know what the value is. So that's your UTXO set. And as you verify transactions, you go through the UTXO set, and, cross out stuff that's spent, and add new stuff to the bottom. Pretty much all there is to it. And the faster this is, the faster you can process a block.
This is like a thin client model, and
So if you have the UTXO set, right, that's a pruned node. It's not thin in the sense that it's less secure, it's just discarded historical data.
and then you need to have the transaction time and the both of that. Do you think this problem is solvable, or that we need something in between,
Um,
like a credit function?
sorry, I'm not sure what you meant there.
Well, in the real world with transactions, you have different payment systems. One of them is like we had chip knip, prepaid, or have a credit system. And now we try to put the function in the blockchain for everything. Do you think that's feasible in the future, or that there needs to be another function in between?
Well, I think if you're talking about like this versus accounts and so on, I mean, I think you make a good argument that all these other ways of doing accounting end up being representable by this kind of system with transaction outputs. Because as an example, I mean, I can define an account to be, go through this set and just add up every output that has the same script quote key. And that is just the representation of my account. Whereas under the hood, I mean, even if you tried to keep an account balance system, where like you had a list of account balances, as it turns out, to make such systems work, you have to have transactions. And once you have transactions, you might as well implement this type of system rather than bolting on transactions on top of an account balance. You know, the reason for that comes down to like how the crypto works, which has been involved, but you know, essentially, you know, any action on an account, you don't want that action to be possible to perform twice. You know, like if I go sign a check, right? If that check didn't have a sequence number, in a cryptographic system, I could take that data and resubmit it. Everything would still be valid, right? From balance is true, valid, you know, the person sending it's valid, the signature is valid. And if it's all valid, well, how do I know that I have to reject the second check, even though the first one, you know, because the first one went through? It's very easy in a unspent transaction system because every hash is unique, and that's a guarantee in Bitcoin. Whereas in a balance-based system, you need a separate mechanism to guarantee that. Ripple is an example that does this, and they use what are called, I think it was transaction or account sequence. Yeah, account sequence numbers, and like every time a transaction is posted to an account, the sequence number increments. Well, by the time you have that, I mean, that's the sequence number too. It's, you know, that's the current state of a balance. I mean, they're the same system. It's just one is more complex than the other. And all the complexities in the stuff where if you get it wrong, the whole system falls apart, right? Whereas in this model, if you want to extract a balance from that, if you or I do it in somewhat different ways, that's okay. You know, the underlying consensus system doesn't break.
But Ripple is centralized, isn't it?
Well, that's an interesting question. Ripple, the way Ripple works is, and Ripple doesn't make it very easy to find this out, but it does have a blockchain under the hood. You know, it's a series of blocks and blocks of transactions, and then the transactions move money from one account to another. Now, Ripple says that they have validators in the system, and everyone can pick different validators. But you know, if I have a different set of validators than you do, the validators I trust can come to a different state of consensus than the ones you trust. And if that's true, well, you might go send me a token representing a house, and I'll think it's valid, and you'll think it's valid, but you think you got the house, and I think I got the house. You know, this is really bad and creates incredibly strong incentives for people using Ripple to all use the same validators. So yeah, I mean, in theory, it's not centralized. Anyone can use their own set of validators, but you'd be crazy not to just use Ripple ones. So, I mean, Ripple people say it's decentralized, but I'd say the social incentives are so strong that it's centralized. You know, whereas in Bitcoin mining, because the definition of validity is about total work, you know, anyone can participate in that. Anyone can contribute to the consensus. You don't need prior permission. And there's no reason for you or I to contribute to a different consensus because the rules very strongly encourage us to work together. You know, on that basis, let's say it's decentralized. But
If you by chance had any time to look at the big chain DB?
Yeah.
yeah, I did, and it wasn't really clear to me what the heck they were actually doing.
They're using a non-ACID database to scale to shit.
Yeah, I don't understand like what they think they're really doing there, because I mean maybe at like a high level. So something that's very easy in all these systems, right, with very high scale, is to do timestamping, right? And all the times, I mean, you sometimes hear this called proof of existence, but timestamping is the more traditional term, and timestamping just means I have data, and I prove that data existed prior to a certain time. And doing this is really easy in blockchains, well, because that has a date attached, and it does for the retargeting mechanism to work. Well, anything here, if I follow back, that series of hash commitments, I know that if this date is valid, anything under here must have been created prior to the date. And the key thing with that is, let's suppose that's our Merkle tree of timestamp data. All right, and I'll say this is January 1st. Right at the millennia. Now, if I know that this was created prior to that date, I know that this was created prior to that date, and I'll say this is sale. Right, so I know the document representing the sale of my house was created that date. That sounds very good. Of course, equally, I could create a slightly different version of this. House sale to Alice. House sale to Bob. I know both documents were created prior to that date, but for the purpose of like registering the sale of the house, that's actually pretty useless. Mm-hmm. Alice and Bob care very deeply about whether or not there exists another document. They don't really care that much about when it was created. That's often not the case. I mean, if you want to prove, for instance, like an example is in a medical study, you might want to go prove that data was generated prior to other data being generated, because first it said a data might be something I could go fraudulently change, right, to correspond to separate research results. Maybe I'm determining like what's the association between this drug and cancer outcomes. So I might collect all that data and then do the processing later. And I want to be sure, as the data is collected, like I haven't changed it, because I will change it based on the outcome of other trials. In that case, timestamping is great, but if there exists a slightly different version of data, that's irrelevant, right? It just means like someone inputted the wrong figure potentially. But that's not true in many cases, and I think big chain DB, if I understand what they're doing, they're much more focused. What they're really doing is more focused on the timestamping, not as clearly focused on, like the consensus side of stuff. And it'd be interesting to see if any of these systems get deployed, like how are they broken?
Is there some slack in timestamping for clients and miners, and how is that solved in the order?
Well, in Bitcoin, the rule is when your node receives a block, it will accept a block provided that the timestamp is less than 2 hours ahead of what you think the current time is. And that's your slack. And it's a little dodgy, but essentially if you're a miner, your incentive is to go create a block that, most people are going to accept as valid. Well, sort of your incentive. There's edge cases here, but that's the basic idea. And I could create a block with timestamp in advance, but most of the network will go rejected. The problem is, in many cases, as a miner, it's actually my incentive to create blocks that people will reject. Because if I'm a miner and I get my blocks, say 95% of the hashing power, and the 5% rejected, those 5% lose out. And their blocks, and the work they do on their blocks will just get orphaned by everyone else, because it's much more likely for the 95% to find the next block than they will. And if I get rid of 5% of my competitors, then I'm making 5% more money, right? Because the difficulty readjusts, and now I'm doing less work for the same amount of money. But we don't really have good solutions to that. I mean, at least in that case, what will really happen is if people start playing with timestamps, the 5% miners will not reject blocks, right, outside of that window. And they'll just realize, well, these guys are just trying to screw me over, so I'll build blocks as well. But, to be frank, we don't have good solutions to this. It's probably one of the most dodgy parts of the entire Bitcoin protocol, dependent on current time. And we have to have it, because otherwise you can't do the difficulty adjustment. But nobody really knows how to do this better.
Could you elaborate a bit more on these 2 hours window? What is that? Is that from the current time up in the future? Or?
Well, remember, there's no such thing as the current time.
Oh.
Right? It's the local current time.
Yeah.
But your node will have a slightly different current time than my node will.
Mm-hmm.
And because of that, at the edge, some things might get rejected by some nodes, but not by others. If everyone creates blocks, within what they think the current time is, and nobody is out more by 2 hours in the forward direction, everything works fine. Now, in the other direction, so suppose I give you a block that has a timestamp 5 hours in the past. That rule does not reject that block. And the reason why that's okay is because backdating the timestamps on your blocks only makes the difficulty go up, which is not in your incentive as a miner. You want to forward date the difficulty to make the difficulty go down. You want to forward date the timestamps on your block, which makes the difficulty go down. Because it looks like more blocks were created, the blocks that were created in more time. Whereas in the reverse direction, blocks were created faster doesn't help you. Now there's an additional rule which says that the timestamp of a block must be at least 1 second in advance of the median time of the past 11 blocks. So it's like you take the 11, you take the median time of that, and you force blocks to advance that. And that rule in reality would prevent me in most cases backdating the blocks a long way back. But that rule isn't that important. And in theory, the way you could do it is you just say that blocks aren't allowed to have a timestamp less than the previous block. You don't actually need the averaging thing, which Pierre Satoshi didn't realize, but it's kind of nice to have some kind of rough rolling average of current time. But we honestly, as protocol designers, we honestly don't know how to go handle this better. And it's just trying to get the real world into these systems is just so hard, because what is the real world? Like, how do you go get something as nebulous as time into a mathematical program? And your only link to the real world is people making claims via hashing power. So, kind of unfortunate there's this potential issue with forward dating, but at least it's not a major attack. I think if you wanted to do a timestamp proof, the easiest thing to just say is, well, whatever this time is at the top of your block, that's probably accurate within a day. It'll be roughly right. If you're trying to do like sub-second timestamping on Bitcoin, you're going to be in a world of trouble. But certainly it's within a day. it's, I think, pretty justifiable.